superconductors without parity symmetry. And after I'm going to review what I did in the first two lectures, I'm going to then change gears slightly and spend a lot of time talking about phenomenological Ginsburg-Landau type theories, after a little bit of talking a little bit more about the microscopic theories. And so what I'm going to focus on are, so when I talk about the Rajba superconductors, I talk about what happens when you put the field on the fourfold symmetry axis. And I didn't talk so much about what happens when you put the field in the plane. And it turns out when you put the field in the plane, you find that you get very easily these sort of epilogue and what I call helical phases appearing. And I'll talk about these two types of phases that show up. And I'm going to focus on the differences between these two phases, and in particular in the epilogue phases you'll find that you have fractional vortices, but in the helical phases you find that you have magnetoelectric effects, both of which can be observed qualitatively, and then also the helical phase can be seen through just junction experiments. Alright, so first, let's just review what we've done so far. I think I've convinced you that the spin-orbit interaction is very important for understanding these broken parity superconductors, and I introduced a specific type of spin-orbit interaction, G of K. And then we went through a relatively long development to come to the first result, and that was that if we have a spin triplet superconductor, that the only possible spin triplet state that survives the presence of this broken inversion symmetry is one in which the d vector, the spin triplet order parameter, is parallel to the g vector that describes the spin wave coupling. All right, and so then we went a little further on from there. We added magnetic fields to the problem, and then we found that if we have what is essentially a spin singlet state, so the order parameter is primarily spin singlet, and there might be a tiny bit of spin triplet there, then we found that the polyter magnetic field is actually formally divergent at zero temperature, provided your spin orbit and your H dot product is zero. So these two directions are orthogonal. And so then we talked about susceptibility, and I told you that the spin susceptibility, which is usually used in centrosymmetric materials to distinguish between singlet and triplet, is no longer useful when you have broken parity symmetry. In particular, you find that the spin singlet spin susceptibility is the same as the spin triplet spin susceptibility in the large spin orbit limit. And here in large spin orbit, this means that the energy scale alpha that describes the spin orbit is much larger than the superconducting gap energy. And then we turn to the limit where we have strong spin orbit, where here we mean with respect to the Fermi energy, so it's getting comparable, some observable fraction of Fermi energy. And then in that case there, we have to treat this as a two-band problem where the two spin-split Fermi surfaces, or the two spin-split bands, become each one band. And then we find that in this particular case, you can get singlet-triplet mixing that leads to S-wave states with line nodes. And so if you remember, the two gaps, the one gap for this band and the one gap for this band, were characterized by 1, 2. And the important point was that I had the spin triplet was the same sign on both bands, and the spin singlet was opposite sign. And the reason you could see that was you can make a spin singlet state by pairing down, up, minus, up, down. And so that gives you your singlet component, and the triplet is the one where down, up, plus, up, down appear. And so that's why this appears. Now, for pedagogical reasons, I actually wrote this formula slightly wrong in the equations. And so as a little exercise, you can see what was wrong when you look at this. I gave you a 2x2 matrix for the pairing interaction in terms of this two-band theory. And I said you should write the gap like this. If you look at it closely, you'll see this isn't right. And I'll let you do that as an exercise to figure out what isn't right about it. All right. And I also had another homework problem, which I might talk at the end of this if there's some time. All right. So now let's turn to today's problem, and that's with respect to epilogue phases and helical phases. And so it may be the case that many of you have not really seen epilogue phases in much detail. So these are Fuller-Frill, Larkin, and Shinnecock phases, and these phases are named after them because they discovered them in, I guess, I think it's the early 1960s. In particular, what they realized is that if you take a spin singlet superconductor, so here I've drawn the Fermi surface for a spin singlet superconductor, comparing a state k up with a state minus k down, If you apply a Zeeman field to that, you split the up and down Fermi surfaces. And so the bands get split, so you have K up is on this sheet, but minus K down is on this sheet. And now you have a problem pairing both K and minus K because they do not lie. So you cannot make a Cooper pair with, you cannot pair on the same sheet of the Fermi surface. So what Fulda-Frel, Markin, and Chinnikov looked for was the possibility that you pair a state K up with a state down at minus K plus Q. So this would be minus K, this would be minus K plus Q here. And they found that such states are indeed stable. And so if you look at the temperature field phase diagram, here's, temperature magnetic field phase diagram, here's magnetic field, here's temperature. They found that in particular, at the very low temperature high field regime, you could get these phases. And so in this particular case then, the Cooper pair order parameter develops a spatial modulation, either e to the iq dot r, because of this Q factor here, or because plus Q is degenerate with minus Q, you can have a linear combination of the two, and you can get a spatial oscillation of close Q dot r. And so in the original papers, Fulda-Frel focused a lot on this particular phase, and Larkin and Chinnikov focused on this particular phase. And it turns out that generically, this phase is the most stable, the one where both plane wave components appear.
So, but may I ask a question to the previous slide?
To the previous slide.
I mean, yeah. So when you write those gaps, right? Well, or here.
Sorry.
What is known as G plus minus psi, right? We assume the pairing on different Fermi surfaces. Why there is no pairing across Fermi surfaces?
Why? You mean why is there no pair from here to here?
Because I guess your parameter preserves this helicity, right?
Yeah. Oh. So actually, the answer does lie in the next slide. So you're asking why can't I make a Cooper pair between this and this red one and this blue one? Is that what you're asking about?
Yes, because when C dagger, let's say plus, C dagger minus, right?
You can in principle, and in fact, that is very similar to the FF pair, right?
Exactly.
Like this, and this. The difference is, okay, I've drawn the picture similar. The difference is the splitting of these bands is on the order of mu BH, and mu BH is typically less than delta. In the spin-orbit case, I said I have strong spin-orbit coupling, so that splitting is much, much larger than delta, and that particular circumstance is not easy to form those phases. In fact, you find those phases are very strongly suppressed. So if you look at this example here, I didn't tell you this, but this field is maybe on the order of 2 times the gap. So mu BH is on the order of 2 times the gap. And you can see that superconductivity no longer exists. And so the spin-orbit coupling is up here somewhere, you're not going to get a stable phase like that.
Wait, but so basically if I put that other parameter right across bars, then it's going to be 0, right? When I solve it.
You'll find that it's unstable because the spin-orbit splitting is too large.
But I might find a system where it's small, and then I'd have to go back
so
to this picture, right?
Indeed, if it's small, then these phases can show up. Exactly.
And then it goes to the previous analysis, the weak spin orbit.
Yeah, and that's
You separated the two, right?
that's true. Though in the weak spin orbit,
The spin orbit is also weak.
yeah, I have to think about how that pops out. But I guess what you find is you will find the low light phases in the analysis when you do this. Okay, so
Wait, but it's different, right? Because here you break time reversal, there you don't break time reversal, right?
sorry, what?
It's qualitatively different still, right? Because there here you break time reversal.
Yeah, it is different. It is different. But you know, the idea of pairing states on two different Fermi surfaces is not necessarily different. But you're right, the symmetries involved are different. All right, so now I want to ask the same question in the broken parity superconductor, what happens? And the reason this is an interesting question is exactly related to this point. So here I've drawn the Rashba two-dimensional case, and so the spins are polarized to this, and you get two bands. When you break parity symmetry and you add magnetic field, you break both parity symmetry and time reversal. And so in that case, you have no symmetries left to guarantee that a state at momentum k on the Fermi surface is degenerate with a state at momentum minus k. And so in fact, generically you might expect that you're going to have always states on your Fermi surface that lie at k and minus k plus some q. And so because you've broken all the symmetries possible that allow these degeneracies, you naturally begin to think, well, here's an easy case where you can find these kinds of finite q states appearing in practice. All right, so in the very next couple slides, I will look at a particular theory, in particular a Rashba spin-orbit coupling. I'll talk about 2 dimensions and 3 dimensions, and I'm going to go over this very quickly just to show you the main results. And we're going to apply a field in the plane, and we're going to see what happens. And this is a relevant problem recently because of this observation of ferromagnetism and superconductivity in these lanthanum luminate strontium titanate interfaces where you have these 2D electron gases. And in fact, people have very recently done work along these lines in these papers, theoretical work. All right, so just to give you a very quick idea of how this is done. So again, I'm going to have a pairing Hamiltonian. Okay, I'm going to have my usual Hamiltonian. I'm going to have a kinetic energy term. Now, the difference I have from before is I'm going to have a pairing term. I'm making this S-wave pairing just because the physics I'm interested in is true for all pairing symmetries, so you may as well do it for S-wave. And then, in addition, I'm going to now for the possibility of having finite momentum in my Cooper pairs. And so now you can see that I have to add a Q label corresponding to this finite momentum of the Cooper pairs. So that's what's showing up here. Now you can go essentially to the same process. Of course, I add a Zeeman field and I add a spin-orbit field as before. You can go through the same process. It's much more complicated because of this finite momentum. Your Green's functions don't carry a single label k, but they carry 2 labels, k and k prime, and you have to solve for that system of Gorkoff equations. But it can be done. One very important parameter that shows up in the microscopic theories, in fact, it's pretty much the only parameter that shows up, is the density of states differences on the 2 Fermi surfaces. So I have 2 bands. I say the density of states on one band is n1, the density of states on the other is n2. And so this delta n is just the difference of those 2 density of states divided by the total density of states. And you'll see that parameter coming up a couple of times. All right, so without going into the details of the microscopic theory, it's actually very easy to understand how come an in-plane field supports these helical phases. All right, so here I've gone from just a normal centrosymmetric material with 2 spin-degenerate bands. This means no asymmetric spin-orbit coupling. I didn't use that language before. That's what the A stands for. And now I apply the Rashba spin-orbit coupling. I get my spin states that run tangential around each band like this. And I get 2 bands coming out of that. And now what I'm going to do is I'm going to apply a field in this direction. So here, in the plane, in this direction. And I'm going to tell you what happens to these bands. You find that one band moves up away from the center of the Brillouin zone. The other band moves down away from the center of the Brillouin zone. And I'm going to convince you that right here, because this is a couple lines of algebra, so it's easy to do. But you can see now right away why you choose these finite momentum pairing states. Because if I was to pair through the original center of the Brillouin zone and take some state here, and pair through this, I'll always not end up on the Fermi surface. But now if I pair through the new center of this band, you can see I can pair every state on this band here. So I can pair this minus this state k plus q with minus k plus q. Both these states lie on the Fermi surface. Similarly here, I can pair this state with this state. I can pair every state on this Fermi surface. This is different than the FFLO case. In the FFLO case, it turns out a single Q could pair maybe one state and one state, but the same Q vector could not pair every state on the Fermi surface. And so you begin to see why these states can be more energetically favorable when you break inversion symmetry. All right, so the crucial bit to this argument is that the bands shift up and down when I apply a field in the plane. And so I'm going to show you that, because once you believe that, and I think that this next bit follows quite nicely. All right, so it's easy to see where this comes from. Your quasi-particle energies in the presence of both the spin-orbit field and the Zeeman field can just be written. This is an effective total magnetic field in some sense. And so you get plus or minus this total effective field. The spins will be polarized parallel and anti-parallel to this. And so now what I'm going to do is I'm going to imagine I have strong spin-orbit coupling, and I'm going to imagine I have a small Zeeman field with respect to that. And so the Zeeman energy will be small, and so I can just do a Taylor series expansion with respect to small mu b over this particular parameter. And then I get my usual case in 2. Here I'm focusing on 2D, so the magnitude of gk actually turns out to be constant, so we can just say alpha is alpha. But the correction term to the Zeeman field is mu bb dot g hat k. So I get a dot product between b and g showing up here. Alright, so that's important. You can see that comes from the magnitude here. And now I look at the structure of G of K for a rational spin orbit coupling. Well, if I apply the field along the x direction, if you remember, my G of K was x hat ky minus y hat kx. And so if I apply the field along the x direction, I'm going to pick up a ky component for the from this dot product. And now you see what happens. This term here essentially leads to a linear term in ky. And so if I just add that here and complete the square, that means formally I must shift my band in ky. And so that's the origin of the shift. And so now you can see the origin of these helical phases showing up. And so you expect to see these kinds of phases when you apply the field in plane. An interesting point, though, is that you can see that while this upper band prefers this q vector that's moved up, the lower band prefers this q vector that moves down. And if the densities of states of these two bands are comparable, it's not clear which one of these is going to win. And you may in fact get linear superpositions of these two q states.
Sorry, two questions.
Yeah.
For 2D, this is clear. If I have 3D and G vanishes along a particular direction,
Yeah.
as it usually does, does it
Yeah.
change that?
It doesn't change I mean, you'll get some smearing effect, but it doesn't change the quality. So you'll get some region, there'll be some plane of the surface for which you compare every state, and then it gets a little bit worse as you move up and down the sphere.
So the phase space is not big enough to change quality.
Yeah, the phase shift doesn't really change quality. Yeah, it doesn't change qualitatively. And in fact,
But in 3D you have to take into account the orbital effect.
yes, that's true. And I should point out, I'm ignoring the orbital effect in all of this.
No, because you're in plane, right?
In 3D, yeah, in a true 3D spherical system, you still would have to include the orbital effect. But I am ignoring that. Just for sake of arguments, you can include it later because you can do chronological theories and then you can include it easier. So,
But if you do two-dimensional system, right, you could still do this.
in principle. All right, so let me jump to the solutions. These are actually 4 3D systems because the way that we did the theory, it turned out that this field was extremely large in 2D, and so we didn't want to, so it just made the calculations a little bit easier to work in 3D. All right, so here are the results. So what you find in, if you have the two density states and the two bands equal, then you find you get 3 phases. You get a uniform superconducting phase. You get a helical phase where you just have one q component, e to the I q dot r showing up, and a multiple q phase where you have many q components showing up, e to the psi 1 e to the I call it 2qr, and then psi 2 e to the minus I 2qr. All right, now, if you allow for a small difference in density states of the two Fermi surfaces, you find a qualitatively different phase diagram. You find that this multiple q phase where you have more than one plane wave solution showing up shows up in this region here, and then the single q phase shows up everywhere in the phase diagram. And so the interesting thing that shows up when you do these calculations is that you find typically 2 orders of magnitude for q. So in this case and up here at 5 fields, you find that q is on the order of UVH over VF, and that makes a lot of sense. But then in this low field regime, you find that q is on the order of delta n UVH over VF. And so here it's a factor 20 smaller than this q. And this really strongly suggests that there are 2 origins for these kinds of possible phases. There's a large q origin and a small q origin. And what I want to go to next is what is the origin of these 2 different magnitudes of q in these phases. And then also what I'm going to go to next is how do you tell the difference between this phase and this phase? And you find out that there are actually very strong differences between these 2 phases.
Daniel, I'm sorry. Is this a description that would give me back FFLO if I took alpha to 0?
Yes. If no, I'd be careful because this is actually done in the large alpha limit. So it is a calculation where I have done this expansion that G is much smaller than alpha.
Okay.
So no, it won't reproduce the effect.
Can I ask a question?
Yeah.
Yes, sir. In your previous slide, you have G of K, which depends on Ky. And Ky on the Fermi surface, yeah, so actually the shift depends on where the momentum is. So why do you have constant shift?
Oh, it's just so I mean, it's just,
No, KY, I understand, but if you look at the Fermi surface, well, the Fermi surface has different KY. I mean, that's a Spinozzi coupling, so it does
Yeah.
depends on the magnitude of.
yeah, I mean, well, we can talk about it, but it is actually just a shift. I mean, so this has got a KY squared term, and so then you can just absorb this term into the KY squared, KY minus something squared, and then you see this KY goes away.
Intuitively, I mean, your arrow, the red arrow is a spin. In the,
Yeah, this red arrow is a spin.
it's a real spin basis, right?
Yes.
So the Zeeman coupling,
Yeah, I haven't put the spins here because it does tilt them a little bit, but it does tilt them. So it's going to give here, it's going to put a little bit of spin in this direction for all of them.
if I'm working on some kind of lattice version, not a spherical or a circular Fermi surface, I probably won't be able to put that KY inside a script. I cannot.
Yeah, you know, you're right. So then there will be some sort of shift. There must be, because you can always go to the small k limit, and so near the zone. But you're right. You also get a deformation of the second band as well. Absolutely. Yes. All right. So what I want to turn to now is the origin of these two different phases, and the simplest way to see it is through Ginzburg-Landau theories. And so here I've written the Ginzburg-Landau theory, where the idea is that you have a second order phase transition, and at a second order phase transition, the order parameter vanishes, and so you can carry out a Taylor series expansion in powers of the order parameter, and it's sufficient to keep the quadratic term and the quartic term, but you also have to allow for spatial variations of the order parameter. What you find is if you calculate, so if I let these parameters be functions of temperature and the Zeeman field, what you find is that if you calculate these two parameters at the point at which this FFLO phase shows up, you find that exactly at that point, K of capital H and beta of H becomes 0. So for lower fields, capital H is positive, and that means the system doesn't want to have spatial fluctuations, but at higher fields, this changes sign, and suddenly you want to introduce spatial fluctuations here. And then you have to add higher order terms to make sure your free energy isn't on bound below, but you can do that. And you find that because both these coefficients change sign, the natural solution is one where you have two plane waves, e to the IQR plus e to the minus IQR. And so this is the origin of the large Q type phases. In broken parity superconductors, something interesting happens. And in particular, what happens is that your Ginzburg-Landau free energy is allowed to have new terms that are by symmetry. In particular, you're allowed to have this term here, which is known as a Lifshitz invariant. And just to see that, loosely speaking, this is like the magnetic field cross the current, the usual superconducting current, B cross S. And what happens in broken parity cases is that your free energy does not need to respect parity symmetry, but it does need to respect time reversal symmetry. But both magnetic field and current are odd under time reversal, so this cross product is even under time reversal. Current is odd under parity, but that's allowed. And then you can see that this particular linear combination is allowed for rational spinoric coupling case. These kinds of Lifshitz invariances depend in particular on the detailed symmetry of your system, but the fact that you have a new term in your Ginzburg-Landau free energy tells you that you're going to get some interesting physics emerging from that. All right, so what does this term do? Well, it's easy to see, and I tell you the answer here. So you find that you automatically get these e to the IQR phases the second you have a non-zero field. All right, and just to show you that, because it's an important point.
Sorry, David. So the implication is that the coefficient is proportional to the density, to the difference in the density of states?
Yes. Though I don't explicitly say that anywhere. All right, so just to show.
Press the first button first.
The first button
Yeah.
here. Okay.
So figure it out. He figured it
So all I'm going to do is just a simple calculation where I put this form into this free energy and then show you that Q must necessarily not be zero. All right, and so let me not look at the total free energy, but the free energy density, and only keep the terms that depend on Q. So that's in particular this term here and this term here. And so when I put that in, I get 2 epsilon z hat dot b cross q. And then I get also plus kappa q squared. And this whole thing then will be multiplied by psi 0 squared. All right? And so now I require my free energy to be minimum with respect to Q. And right away you can see what comes out. I've got a linear term and a quadratic term, and therefore I must get a non-zero solution for Q. And since we want our system to be minimized with respect to all 3 parameters, that tells us that Q must indeed be this value. This exercise is good too, because it tells you something else that's important. It tells you that even though you have such a phase, this phase carries no current. And simply the reason is the current is formally given by the derivative of the free energy with respect to Q. I've set that to 0 to get equilibrium, and that gives me this Q vector. So only deviations from this Q vector will give you a current in this phase. Did you have a question?
Yes. So in this Rashba system, the transition, you say transition into an FFLO, the transition is immediately for any infinitesimally small...
No. As a function of the Pauli field, you find you get this crossover. So it's a relatively, as a relatively large field. So in particular, on the order, when UVH is on the order of delta, that's when you get this change of sign.
And this stabilizes...
For all fields. This is for infinitesimal fields. Q vanishes as B goes to 0, but it always exists. All right.
And does this term stabilize the change of sign?
So then it becomes a little bit complicated to actually work that out, because you need to add this, you need to include, it doesn't necessarily stabilize the change of sign of kappa. That will still happen. So the change of sign of kappa does happen when I have this delta n equal to 0. And so that large Q phase is coming from FFLO type physics, where this term changes sign. The small Q phase is coming from the appearance of this new term in the Ginsburg free energy. All right. The interesting thing as well is that since this helical phase, or this phase, shows up because of a new term in your free energy, that suggests that this phase is not going to be strongly dependent on impurities. And so if you know something about the FFLO phase, you know that these are easily destroyed by impurities. But now you have the possibility of having something that is not so easily destroyed by impurities. And very recently, this has been studied in the context of two-dimensional electron gases. So I should point out, many people have studied these helical phases, but very recently, in fact last week, the MIT group put out a paper, a theoretical paper, on these lanthanum-aluminate strontium titanate interfaces, where what they calculated was the critical field for these FFLO type phases as a function of the elastic disorder scattering rate. All right. So for very small disorder, they get the kind of picture I was talking about, but it turns out in these systems, disorder is an important parameter. And so what they find is that at very small disorder, and in fact many people have found results similar to this, is that you have a critical field which is on the order of the spin orbit energy gap, and in units I'm talking about, that's 2 alpha. So if you remember, that's my spin orbit energy scale divided by the 0 temperature gap. And so in large spin orbit cases, this is a gigantic value, right? So this is much larger than the usual Pauli field. And so you see these fields are well supported. But then what they found, and in fact other people have studied this problem as well, is when you add disorder to that, this field gets rapidly suppressed to something on the order of the Pauli field that you usually get in conventional superconductors. But what they found in their result, which is new, is that if you go beyond that, you actually get a substantial enhancement again of this critical field. And you find that for elastic scattering rates on the order of the spin orbit gap, you find that this is on the order of the square root delta S0 over delta. So the spin orbit energy gap over delta 0. So this is a very large scale. And this is important because in these materials it's believed that you have magnetic fields. And it's a good question to understand. So you have magnetic early order, and it's not clear why superconductivity survives in the presence of ferromagnetic order, so they're suggesting that this is the reason why in these large critical fields, even in the presence of disorder. All right, so now what I want to turn to are the differences between these two phases. So we have this FFLO-like phase and we have this helical phase. How can you experimentally see the difference between the two? All right, so first is the FFLO-like phase. And so again, I want to make a simple point here. I want to now turn again to Ginzburg-Landau type theory and say, well, in the FFLO-like phase, I have two components to my order parameter. I have for a modulation e to the IQX and a modulation e to the minus IQX. And so now I can, instead of expanding in psi, I can extend these two new components here, and I can write down a free energy density for that. So as usual, you require all the usual symmetries, time reversal, age invariance, and in addition now you enforce translational variance. But the one thing I want you to notice is when you look at this free energy density, all I have is magnitude of psi qx squared and magnitude of psi minus qx squared. Nowhere do I have a term that looks like psi qx times psi minus qx complex conjugate. All right? And this immediately implies that this free energy has a u1 times u1 symmetry. I'm free to change the phase of this component separately from the phase of this component. And that's very important for vortices because if you remember, usual Ginzburg-Landau free energy has just a u1 symmetry, and that u1 symmetry is what gives rise to vortices. Here we have a u1 cross u1 symmetry. I'll make the comment that in the case of multiband superconductors, people have looked at theories with u1 cross u1 symmetry, but there you never truly have it. And in fact, it's come up a little bit in the talks before. You always have this interband Josephson coupling term, and that destroys your u1 cross u1 symmetry. Here's a case where you do truly have it. And because I'm running a little bit out of time.
So why don't you have this coupling term?
Yeah, that's what these two are about. But I'm not going to, you guys can read through the algebra here, but I'm running a little bit out of time. So what I'm just going to say is that if you combine gauge invariance and you impose translational invariance, then you find, in fact, that you cannot have any term that has psi qx times psi minus qx complex conjugate unless you can only have the magnitudes of psi qx and psi minus qx. That's what this little bit of algebra is looking at, and you can look at that later when you look at the notes. All right. So this is a symmetry of your system. So how much time do I have left?
You have about 3 minutes.
3 minutes, okay. All right. So I think I'll have just enough time to make this last point, actually. All right. So in the standard Ginzburg-Landau theory, you know, the free energy has this U1 invariance, and so we are allowed to consider solutions of our order parameter where we have a phase winding in the phase, right? So we have a magnitude, and then we have n times the phase winding. This means that as I circle a defect, I pick up n times 2 pi phase factors. And then you can do the calculation of the current of such an object. And in fact, that's what Agterberg did early on. And the current is just a quantum mechanical current. And so what I've done here is I've allowed gradients of this order parameter to show up, but I've also now included a vector potential because we have a superconductor. Now, very far from any vortex 4, so here's your vortex 4, pushing the order parameter to 0, but far away it's approximately constant in magnitude. Very far from the vortex 4, the current must be 0, and so then you can do a simple calculation where you just calculate this in a line integral on the trajectory around the vortex 4, far away from the core, and you find that this portion gives you the flux enclosed by the vortex, this gives you a factor of 2 pi, and you find that the flux enclosed by a vortex is quantized. And so this is the famous result of Agterberg and others afterwards. And so in particular, you find that you're quantized in terms of the usual flux quantum here. Now if we go to the U1 cross U1 symmetry vortices, in particular, I now have U1 cross U1 symmetry. I can allow a phase winding of n in one component and a phase winding of n in the other component. I can ask the same question. What is the flux enclosed when I say wind this by 2 pi, but keep this approximately 2? All right, and so let's just do that. Let's consider a 1-0 vortex, but far away from the vortex, the magnitudes of the order parameter are psi 1 in the first component and psi 2 in the second component. You find that this is quite generally the case in this FFLO-like phase. So now we can do the same thing. the current now is the contribution of this term and this term. It's just the sum of the two. But because this has no phase winding, it's approximately stationally constant. And so this doesn't show up in this term here. The vector potential still couples to both components, and so both components show up. And so now when I require the current is 0 far from the core, and I do this line integral, I found that the flux enclosed is different than the usual flux quantum. It's multiplied by this factor here, psi 1 squared over psi 1 squared plus psi 2 squared. And so you find that these FFLO-like phases support fractional vortices. And so that would be one way to identify this phase showing up in these systems. Incidentally, if you're interested in the actual FFLO phase, then these two are of equal magnitude, and so there you find that the vortices are actually 1/2 of flux quantum. All right, so that's one qualitative observation for the FFLO-like phase. I'll just mention that for the helical phase, there are actually quite a bit coming from this Lifshitz invariance, particularly because this couples magnetic field and current, you get magneto-electric effects. And I'll leave this here so you can actually read through it, and then the other thing you can do is do just an experiment to look for these phases in the helical phase. That won't work as well for the FFLO-like phase. So those are the points I wanted to make, so that's, I guess, a good place to stop.
All right, thank you. Questions? Comments?
Maybe a naive question, but these Ginsburg-Landau free energies and these extra terms, these Lifshitz invariants,
Yeah.
so you just write them down because they allow the symmetry, or
Yes.
you derive them from microscopic?
You can also derive them from microscopic theory, and this is actually what Ilya asked about. It turns out this Lifshitz invariant is proportional to this delta n factor. So that's relevant. And I didn't mention this before, but it is possible to have delta n equal to 1, and that's exactly this case of the surface of a topological incident of superconductivity. In that case, delta n is actually 1, and so then you always get this helical phase showing up.
To observe this fractional vortices, so
Yeah.
you need to be the strong spin-orbit captain unit.
Yes. Well, no, you need the FFLO phase only, because it even happens in 0 spin-orbit coupling when you have an FFLO superconductor. So there's nothing. Yeah, I mean, the phenomenon.
You need two components, psi 1 and psi 2.
Yes, but these two components are just. Are just spatial modulated components, e to the IQX and e to the minus IQX. And so in the actual FFLO superconductor, so not even in these other FFLO cases, you do have exactly that. You have e to the IQX plus e to the minus IQX. But in principle, you should teach each component as a separate degree of freedom. And then you get this two-component theory. So even in FFLO superconductor, so prediction is there, you get exactly 1/2 quantum vortices. But in these non-central symmetric cases, they can differ from 1/2. You can get two different types of fractional vortices whose sum is one usual flux quantum.
And in your case, when you have this, so when you have some spin-orbit captain, you have that related. You are in this FFLO regime when it's a difference in density of phase is exactly 0 or
Yeah, so
it's very big.
it's not very peculiar. So
the question
it's,
is
yeah.
it very unstable or?
It's as unstable as the FFLO case, actually slightly more stable than FFLO in the usual case. But what you find is here you find the FFLO phase everywhere when delta n equals delta n1 equals n2. But as you increase delta n, you find the FFLO-like phase, that's this phase here, gets smaller and smaller. And in fact, as you push delta n to 1, you find that this phase entirely disappears. And in fact, it will entirely disappear. And so in non-central symmetric cases, this phase exists in clean systems. You'll have it, but these interfaces are presumably not clean. So in interfaces, you expect actually this helical state probably everywhere.
What is actually the experimental situation?
That's a good question. I mean, so it's, okay, this is a preprint that came out last week in case of in the interfaces. And so at the same time, there was a physical review letter that said that they observed ferromagnetism and superconductivity in the same samples. And really the question then becomes, are they actually coexisting in the same region, or is it some kind of in different regions? And I'm not, oh, you know an answer to this?
Well, yeah, at least I've seen data from CAM-MOLA.
From who?
So basically you go around over the surface of the sample and you find some pieces of it are ferromagnetic.
Oh, really?
And
Okay.
some pieces of it are diamagnetic. So it does appear that it is not, well, it is coexisting in the sense that it's lumpy, but it's not in the same place.
It's not in the same place. Okay, so then that could be another reason. So then you could apply fields to these materials and look for these kinds of phases, because the helical phase should still appear.
There are these fractional vortices, Saltz and Eschrick, I think, published a series of papers saying that they have a multi-component general order parameter. Sort of similar argument, right? There can be different windings and different components.
Yeah.
They had some complicated classification scheme for what kind of fractional vortices are allowed and which are not. And so I just, since I don't remember it, I was wondering whether I could compare what kind of fractional vortices one theory allows versus the other.
Yeah, so in their case, what mattered a lot was the angular momentum of the Cooper pairs. And so then you could combine the angular momentum of the Cooper pairs with the actual orbital winding, and then through that, have some kind of total angular momentum effect, and then use that to classify the types of vortices you have. I mean, here it's qualitatively different because it's coming from, I didn't mention this, but you can ask where is the rest of this vorticity showing up? Because I have a half vortex, that means if I go around a defect, I only have a phase winding, an overall phase winding of say pi. Whereas the other half of the phase of the, when you go around the topological defect, you have to come back to the same phase, or to the same state. And yet I'm only saying that the total phase is only winding about by pi. You ask where is the rest of the phase going, and it turns out that what happens is, in these phases, you actually develop a periodic lattice. And if you remember, if you know anything about your periodic lattices, you can have dislocations as topological defects of these periodic lattices. What happens is, in fact, you're introducing half a dislocation, which gives you an additional sign change of pi with a half vortex, which gives you a sign change of pi, or a phase change of pi, and so the total change is in fact 2 pi. So it's a combined defect, which is a mixture of dislocation of the usual translational symmetry breaking and the vorticity of the usual superconductivity. So in that sense, it's different from what, but yeah.
Right, I agree, it's different in physics. What I was saying is somebody comes and says, I observe fractional vortex with, 45% of the total vorticity. Can one tell whether it's possible within one theory but not the other? Because in your case, it seems to me, because it's a ratio of the amplitudes, you have more flexibility than they do.
Yeah, you can get any value. I mean, to get fractional vorticity, you have to break time reversal symmetry in some way. And so, in fact, fractions other than 1/2 of flux moment. So it turns out this phase actually breaks time reversal symmetry once the two components psi 1 and psi 2 are not the same magnitude. If they're the same magnitude, then I just get a cosine QR, and that's purely real. And so that doesn't bring time reversal symmetry. But if I have them different magnitudes, then I will not be able to go back to the same factor under a complex conjugation.
I'm just remembering that there are reports of fractional vortices at high TC grain boundaries. Is it possible that local symmetry breaking is inducing stuff like this?
Those are half vortices, right?
Well, there are certainly half vortices, but there's a distribution of flux things that are identified. It's hard to image exactly how much it is.
Yeah, so what happens at grain boundaries? I mean, what's essential there is, again, the phase change of the superconducting D-wave order parameter. And then I guess at a grain boundary, you can connect perhaps different phases. And then it becomes maybe, then I think you have to look at the details to really, I'd have to look again at the details to figure out exactly how those pop out. But those are the essential ingredients. I guess the grain boundaries must introduce different lobes of the D-wave order parameter, that allows you to have some phase change across there, and then when you complete the circuit, you have to compensate for that in some way. So how you get fractional vortices, I'm not exactly sure, but maybe there is, maybe because you're not actually looking at isolated ones, you're looking at many of them, and you don't get perfect screening, for example, or something like this. Not a satisfactory answer, I realize, but it gives you some idea.
Complicated problem.
Other questions?
So you were mentioning that, in fact, to find this full lateral LO phase is very difficult. You have to go to very high magnetic fields. And for instance, helical phases, if you have impurities, they get suppressed. You were mentioning.
The helical phase, well, this survives the FFLO-like phase, does not survive impurities. So that gets, so maybe it's useful to look actually at the picture that these guys calculated. If you look here, you can see there's this very strong suppression for small impurity scattering, right? And this impurity scattering is actually destroying the FFLO phase until suddenly the helical phase is all that's left over. And then as you go on, the helical phase emerges stronger. And so that's what's happening. This is FFLO. That's what I think is happening. There's no calculation to support that. That makes sense.
So my question is, the people that work on ultra-cold gases,
Yeah.
they claim they can see this
FFLO phases, yeah.
Exactly, and my question is, what is the state of the art? In fact, they have no impurities in principle.
Yeah.
So this phase is there really clear. Do you know more about the situation of these experiments?
Yeah, so let me, I do because I read a little while ago, and I have to remember what I read. So I know that they purposely tuned the system to be as close as you can to FFLO, and in particular they made their systems quasi-one-dimensional, which actually strongly enhances the phase space for FFLO. And I guess, what did they exactly see? So they haven't seen the Q vector, right? So if you really want to see it, you want to see the Q vector. What they have seen are, right now it's escaping me, but they've seen evidence that's consistent with FFLO. Right now, I have to go look in the papers here. But okay, they haven't measured the Q vector to be proof of FFLO. They've only seen, they've looked at the excitation spectrum of FFLO states, and you see something consistent with that excitation spectrum.
But they never went to this helical phase.
No, they can in principle, and in fact, it's interesting that last year this helical phase has been rediscovered in the context of cold atoms as well. When you have these spin orbit coupled cold atom systems, you can find these phases. And so it's sort of a theoretical idea now, only the last year or so people have been looking at it, and so experimentalists are now adding this spin orbit coupling to the cold atom systems and looking. So in principle, they should be able to see that.
So possibly ill-posed question, but so do I correctly understand that if this, if you have a spin orbit split Fermi surfaces, right? Then you try to use impurities in the sample, and the qualitatively the role of magnetic and non-magnetic impurities is going to be the same, right? No, because I'm both.
Okay, for normal state properties, okay.
No, for superconducting, right? Because both scatter kind of across Fermi surfaces, because Fermi surfaces are mixed fields, right? It's probably the phase only difference. Right?
So maybe, okay, it's not so straightforward. I'll tell you why. So in particular, I can, by making the spin orbit cap vanish here, make a usual spin singlet superconductor from exactly this language. There's no reason for me not to choose this particular spin basis at every point in K. All right, and then I can introduce a gap with this in this chirality basis. I can solve the problem because we have complete spin degeneracy in the limit that there's no spin orbit coupling. And so in that case, you know very well that when you add magnetic impurities, the TC of the S-wave case is strongly suppressed. And so it's not obvious that when you have now even the spin orbit coupling, when there's a way you can reproduce the usual singlet limit, that when you add magnetic impurities, they're going to have no effect. They're going to have some effect. And it's a complicated issue because they're going to have, I mean, you've seen this complicated issue in two-band superconductors. All the complications that show up there show up here as well.
But I think, right, the time reversal is not broken. So
Yeah,
magnetic,
yeah, that's right.
non-magnetic is there. However, if
That's-
you go to the helicity basis, what Leibniz is saying, then of course even conventional impurity, because it scatters by finite k, in case of spin orbit, will not conserve spin. Right? I mean,
Yeah, so then you add two. Is that what you meant actually? That you had,
Yeah, because impurity is coupled to spin, but not to helicity, right? So since spins also mix, right? So it's kind of probably doesn't
yeah,
make
it
sense.
becomes, yeah, so your impurity scattering potential becomes something non-diagonal on the helicity basis.
So basically P is coupled to spin, and since I scatter by some momentum, I do something to the spin.
Yeah, exactly.
And that goes. All right, I think this is a good point to thank Daniel again. Go and have coffee.